Problem solving using energy methods. This is a class summary. Problem solving using energy methods is a great choice when you don't have the time, don't need the time, or it takes off from an angle, lands at an angle, but you don't need to know the information about the angle itself. It'll kind of simplify some of the solving methods. To begin with, let's look at a simple problem. I've got a car going down a hill, starts off at 65 meters at an unknown speed, goes down to 52 meters in height at 18 meters per second, and then at the bottom I've got two stopping forces. I have F1, D1, so I have a force and a distance associated with it, and F2, D2, a different force. My goal is to find the speed after the second stopping force has been applied for 4 meters. I'm going to use the concepts of conservation of energy, so I don't need time, and I'm going to use this by comparing the total energy at two locations. One location is dictated by the question. In this case, it's 4 meters into the second stopping force, F2. So F2 is there, and 4 meters is the blue circle. The second location must be where you know the velocity and the height compared to the first location. So at first glance, it looks like I have a choice, 65 meters and 52 meters in height. But in reality, I only know the speed at one of those locations. So I only know the speed at the 52 meter height. So that's going to have to be the choice that I compare to. So now I've got my two locations. I'll look for any forces other than gravity that act anywhere between these two locations. In this problem, I've got F1 and I've got F2. I've got two forces that acting against the motion. If there weren't any other forces, then I would only use kinetic and potential energy due to gravity. Otherwise, I'd use work-energy relationships, which is my choice here. So here my problem sets up. Now I'll start going through the solutions process. Total energy at the top of the ride equals total energy at the bottom of the ride. This would be a great first choice if I didn't have those other forces, F1 and F2. But I do have those forces, so really that's not going to be the complete choice that I need to make. Instead, I'll start with the total energy at the top of the ride. Now I've got to look at these outside forces, F1 and F2. Well, F1 is going to the left and the motion is going to the right. So in this case, we would say work is being done on the vehicle. Whenever work is being done on the vehicle, the object, or in this case the car, then we subtract it from where the starting energy is located. So total energy at the top of the ride where it starts, minus the work of F1. Now F2 is the same situation. It's going left and the motion is going right, so this is work being done on the car, so I'm also going to subtract it. And then I'm going to set them equal to the final energy, which in this case is just total energy at the bottom of the ride. Now I need to be a little more definitive on my energies. Kinetic energy plus potential energy minus work of F1 minus the work of F2 equals kinetic energy plus potential energy at the bottom of the ride. Well, if I start looking at it, I've got 1 half mv squared plus mgh minus the work of F1, which is F1 d1, minus the work of F2 times 4 meters. Now at the bottom of the ride, I don't have any motion, so there's no kinetic energy. I've come to a stop after 4 meters according to the picture's description, and I don't have any height. So that's also 0. So that's why the 0 is on the right-hand side. And if I put in some numbers, I can see that I've got 1 half 550 kilograms times 18 meters per second squared plus 550 kilograms times 9.80 meters per second squared times 52 meters minus F1 D1 F2 times 4 meters, and all that equals 0. So at this point I'm going to stop the solution process. Everything's pretty much set up. I need some numbers that are given in the problem for F1 and D1. And typically in a word problem you might have those numbers, so you wouldn't have one equation and 3 variables. You have some numbers to put in there.